Hello. So I wanted to send out and make this quick video to talk about the problems that we were running into with class activity 16B, which was building a buffer with the MOSFET. So first of all, let's look at what we had. So we had this IRF 530, and we were trying to design it to have an output of 5 volts, which is halfway between the 10 volts and the ground, and we wanted to have 10 microamps in order to have an R out of the 100 ohms. So if we run this, we look right here and see that we have a current of 10 microamps, which is exactly what we wanted. I look at the voltage and you see we're at 5 volts, everything's great. So it seems like it's doing exactly what we want. The problem is that if we look at what produce the gate voltage, you see we have this 8.6 voltage. Well, if I look at the gate to source voltage, you see I have 3.6 volts, which, okay, is that a problem or not? Well, let's go and look at what the threshold is for this MOSFET. So if I look for this MOSFET, you see it has a threshold voltage of 4 volts, but we're only putting in 3.6 volts. So my threshold voltage is low, so my gate to source voltage is less than my threshold voltage. It is in cutoff. Well, let's see what's going on. So if I go back over to this MOSFET and scroll to where it talks about, so here is my cutoff, or you see it's also called subthreshold when VGS is less than my threshold voltage. Well, you see it isn't really zero. It's this exponential thing that's kind of, here's your PN junction like we had before with this thermal voltage, where you see right here it says the IDO is the current right at threshold. So it's going to have an exponential relationship up to threshold, and then if I remember right down here when I'm in active, then it's quadratic. So it has exponential and then quadratic. So we want to make sure, based off of all of our analysis, we need to make sure that we're in active. So we're going to come over here and we're just going to find out what that cutoff point is to be in active. So we're going to come in here and give it a voltage source that is just going to be the threshold point. So this has a 4 volt threshold. So I'm going to come in here and I'm just going to give it, let's delete this for now. Okay, so now my source is 0 and I'm putting in 4 volts. So I run this and you see that it has 13.2 milliamps. So any current less than 13.2 milliamps, and it's actually in cutoff. So we're going to come over here and we're going to say that my ID has to be greater than 13 milliamps. Well, let's just go ahead and look at 15 milliamps. Okay, so if we're at 15 milliamps, we want to look at, you see my R out is approximately equal to 1 over GM, which is equal to 1 over the square root of 2 times KP times ID. Okay, so at this case, we are going to be equal to 1 over 2 times, let's go back and check what my KP was just to make sure. Okay, you see that my KP is 5. So this is going to be 5, and this is going to be 15 times 10 to the minus 3, and then we square root that. Okay, so let's go over and see what that resistance will be. So 1 divided by the square root of 5 times 15 millivolts. So you see that the output resistance will be 2.58 ohms. So this means that my R out needs to be greater than 2.5 ohms. So designing this to have an R out of 100 was never going to work. So it had a bad specification. Well, this is all for the IRF 530. Well, what happens if we change the transistor? So let's go and do this for a smaller transistor. So if I look right here, you see this as a transistor with a high Kp. So we're going to pick a smaller transistor, pick the other one. This is like the ones we're using in the lab, the 2N7002. And in this case, you see it has a threshold of 1.6 volts. So we're going to come in here. Oh, we did change it. And we're going to look at what if I put in right at threshold again. Okay, and you see that it has 0.4 milliamps. So now we're going to do the same thing, and we're going to say that R out is equal to 1 over GM, which is equal to 1 over 2 times the Kp for this one is 0.17 times its minimum current, which is 3 milliamps. So then we're going to come over and try that out. And so we change the Kp to 0.17, and we change our current to 0.4 milliamps. And you see 85 ohms. So my R out has to be less than 85 ohms. So you can see that if I had a specifications of 100 ohms, this isn't really going to work, and I'm never going to be able to meet the specification and still keep it inactive. So we have to change the specifications of the problem to get it to work.